Yes.
So now, yeah, is my slide?
Yes, yes.
Is my slide visible?
Yes.
Okay.
Okay, so again, welcome everyone. Good morning. So this is the last session of the workshop, but never the least. So we have our next speaker is Professor Partha Sarati Mandal. He's from Department of Mathematics, but he works in the area of distributed computing, and so you'll get a perspective of predictive modeling from a distributed angle. So, it will be a welcome change for you. I hope you'll enjoy this topic.
Okay, so let's start. So let's start now.
Yeah, you can start, please.
Okay, so my full screen is visible to everyone, right? Ashok?
Yes, yes. So participants, can you see?
Yes, sir.
Okay, thank you.
So please let me know, any of you, if, see, I cannot see anybody. I cannot see because I'm sharing my full screen. I cannot see any pop-up window also. Okay, also if some question will come, please let me know.
Yeah, sure, sure.
Yeah. So thank you very much for inviting me in this series of the talk. And I'm fortunate to be here today, but my area of expertization is not machine learning. My area of expertization is distributed algorithm, and this is the scope I got to learn machine learning, which is now hot topic. And there is a lot of research going on distributed machine learning. I started learning and try to give overview over there. So first of all, I may not be able to answer all the questions, but I try my best to relate machine learning with distributed computing, how machine learning is relevant with distributed algorithm, and which is very much essential in the context of our era of big data. So let's start, and anytime you can stop me if you have any questions. So relevance of distributed machine learning in this context, you know that data set is too big and gradually it is increasing. This is the one context. Another is data is inherently distributed. That is why distributed machine learning is also relevant. Moving data is expensive. For example, you see there is a data collected at a hospital or is an educational center. So now moving that data to other place is expensive. Some cases, the data privacy also does matter. So data privacy may not allow you to access the data, or you cannot allow to move the data to other place. So these are the things why distributed machine learning is coming in the picture. And another final thing is basically to because of big data and now size of data and size of the model, computing in a single machine is difficult. So that is why how to execute machine learning algorithm over different machines which are located in different places or in a parallel system. Okay, so these are very relevant today in the era of big data. So that is why this context is also very relevant. So far, I think you have learned about the basic or the advanced topic on the machine learning. I'm just take some of those equations, and I'll explain the context of the distributed algorithm. Okay. So I would like to thank Eric Zink and Francis Buck. I basically followed their lectures, and they're the big boss in this domain. And so I followed their lectures and their material, and my presentation is based on their lecture notes. So now the scientific context of this topic, you know, the proliferations of the digital data, personal data, industry data, maybe the scientific data like, you know, the research data or bioinformatics to humanities, and need for automated processing of the massive data. So that is the hype term is that big data is basically develop the data science research and the educations, and that also actually thrust into the area of machine learning and then deep learning, and then finally coming to the artificial intelligence. So the recent progress in the perceptions are following: massive data, computing powers, methodology, and scientific progress. So now the intelligence is basically is combining the four terms. One is the model, algorithms. A model means the assumptions. Based on that, you design the algorithm and apply the data, and finally you execute in a computing power. So this is altogether we can term as intelligence. And I will focus today is on the algorithm perspective. So this is the topic today. I look in the aspect of algorithm to solve the machine learning problems and how it is can be done in a distributed setting and parallel setting. So give some overview the how massive data is today. The massive data, you know that the Facebook, everybody using Facebook, there is a 1 billion plus users, and there are 30 plus petabyte of data. Like Wikipedia, you know that 32 millions of pages, and YouTube 100 plus hours video is uploaded every minute, and Twitter is 645 million users and 500 millions tweets per day. So this kind of data is accumulated, okay, and to mine some kind of information over there. So similarly, growing the model complexity, you know that model complexity is increasing in several application domains, such as, you know, that deep learning and Google Brain. So to classify the images, they do have 1 to 10 billions of parameters. And so this is so huge model size. Another is a multitask regression for simplest whole genome analysis. It's basically needed 100 million to 1 billion model parameters. Like another topics, you know, that topic models for new article analysis up to 1 trillion model parameters. And finally, the Netflix give you the video recommendation based on that 1 to 10 billions of model parameter. So these are so now increasing the data size and the model size, and finally now executing a single machine is probably impossible. Even so, that is why in the context of distributed system or parallel system is coming in the picture. So the recent trends is, you know, big data has been a very popular in recent year, and it appeared in many application domains that is already told you. Computational biology, it could be the online advertisement, recommendation system, and so on. So big data generates a lot of values and capabilities for machine learning algorithm, but also create many challenges. Let's discuss about few of the challenges. So this lecture will cover the challenges for machine learning system in the big data era and describe the big picture solution towards the distributed algorithm. So let's discuss the challenges which are very crucial today. So the amount of data grows, the efficiency and effective mining information from data become very challenging because of the size and that location where the data is gathered and their corresponding mining informations. So the fundamental issues arise when the figuring out how to make the computation, storage, transmission, and manipulations of the data happen in the low latency. So there is also theoretical challenges, you know, such as how to design an algorithm that scale but not lose the theoretical convergence of the which is guaranteed. So here is one illustration. You can see the number of machine increasing, okay, and how the processing power or speed up is taking place. So there are three plots you can see, and whether the diagonal lines is basically the perfect, so that this number of machine increasing to analyze the machine learning or predicting something for machine learning. Actually, this number machine increasing and the processing power or speed is increasing, means you can get a very short time, you can analyze and give the output, which is the ideal line. The diagonal line is the ideal line. But the good one is the blue line, which basically it's quite good way it is expected that processing power and speed of prediction is coming in the picture, increases the number of the machines. And if you are unable to design a good algorithm or unable to decompose the tasks into different machines, then your performance, increasing the number of the machine also, will not able to get the good performance. So this is the pathetic, which is showing in the red line, okay, red plot. You see the red plot actually demonstrating that increasing the number of the machine, you are not able to get a good performance, or you are unable to give the good speed up of an algorithm and so on, right? So this is one of the big challenge, okay? So amount of data growth and how to incorporate it with the how to reduce the low latency, how we can get the output in the low latency situation, how give the convergence guaranteed theoretically. So massive data scale is another issue. That the first challenge is a straightforward and which is relevant to the the first challenge is that there is a more and more data. And for example, Facebook has basically over 1.6 billion of active users, and simple computation on Facebook network will need to deal with a graph of billion nodes and corresponding edges among them. Right now, for example, somebody want to ask you in the social network, you try to give some number of employees or some number of scholar who are doing currently PhD in this topic, right? So how do you mine the data from the Facebook, looking the profile of each and every members? So this is a huge task, because you have to mine the data from the huge graph, which is having the size of billion of node and corresponding age. So because of the data size, simple manipulation of data become a challenging, and storing and transmitting can also be the biggest bottleneck of the whole model pipeline. So here is some kind of picture is giving that, for example, Internet of Things use so many devices and how to analyze them. So another thing corresponding to the big data, now coming to the gigantic, basically the model size. As I already told you, the second challenge is similar to and related to the first challenge. If size of data is big and you are trying to predict something, you design a model and increases the number of the parameter. So the size of the data grows, the machine learning algorithm tend to have with a large model to fully capture the information in the data, and therefore model size also grows. And for example, here is convolution neural network can have 1 million of parameters, and efficient model training as well as the inference become very challenging. So you can see that picture where it is classifying the image, that how we can make so the full connectivity among the nodes, and how so here is question that big data needs a big model and to extract the understanding, but ML model with greater than 1 trillion parameter also would not fit in the model. So model changing is also important here in the context of the big data. Okay. Now, finally come to the third challenge, which is inadequate support of the new methods. So that is what I'm talking about, the third challenge. That's the currently we have the scalable algorithm, means if your data or your parameter is increasing. So scalable algorithm, you know that, which are k-means, logistic regression, and those those are basically scalable algorithm. You can scale. And whether there are technique which use the old technique, whether those are not scalable. So some of the recent development software package such as Yahoo LDA and the ViewQual and the providing the newest model, and many packages still only implement classical model, which are not designed for the big data. So there is a scope of designing model which is relevant to the big data. So there is inadequate scalability support for the new method, and it is challenging to provide a general distributed system that support all machine learning algorithms. So here is k-means, logistic regression, decision tree, and so on. So these are basically easy to scale. But these are the old techniques. So now machine learning methods. So let's discuss about that. We'll discuss here some general properties of the machine learning algorithms, and those properties will be useful, and since they will serve as the guidelines for designing general distributed system to scale the machine learning algorithm. So here is everybody that ML can be written in this form, whether you want to basically the equation you can see here where L and omega is basically represent the model, and where xy is basically keep the data, and theta is the set of parameter. You want to maximize this function. So usually machine learning algorithms are solved in iterative fashions, and the parameters are updated based on the data until convergence. So now which part can be done parallelly? Here you look into the figure where we want to maximize this model, and we want to iteratively solve the problem. But this part, you can see this part here, we can compute parallelly. So parallelization is possible here. So there are two basic approaches for parallelizing such iterative technique in the machine learning method. One is called data parallelism, another is called model parallelism. Let's discuss about data parallelism. What it does basically, in data parallelism, data is partitioned and distributed into different workers or the machines, and each worker typically updates all parameters based on its shared share of the data. Okay, so what you have a bucket of data, you divide the data into different bowl. Okay, and the model is run with the data from each bowl. That's the concept of the data parallelism. So you can run parallelly, right? So you distribute the data in different machines, and the same model you can run with that small amount of data. Okay, so that's the data parallelism. You can run it parallelly. Similarly, model parallelism is following that each worker has access to the entire data set, but only update the subset of the parameter at a time. So that is part of the model they are updating. So part of the model in the context that you have a huge number of parameters. Some parameters given to one machine has the access of whole data set. Similarly, another set of parameters given to another machine has the access to the whole data set, like this. So here, another model can be used as like a shared memory model. You can consider that whole data kept in a data center, right? And now every process has access to the data center. They have their model, which is a global model, and access the data or data, and then execute some part of the parameter, some subset of the parameter to compute. Okay, so this concept is called model parallelism. But of course, both the principal approach are not exclusive, and thus also combined to yield a better performance in practice. It's not necessary that only data parallelism may give a better result compared to the model, or vice versa. So now, data in the model parallelism look in this illustration. So here, what I am to say that, so this chunk is basically considered as a model, and in the data parallelism, whole model is given actually, and this is executed with one set of data, subset of the data, right? And which is replica to the different model, like model node 1, node 2, node 3, and node 4. All are separately calculating the model or implementing the model based on the set of data available with the particular node. Okay, and whereas the model parallelism in the picture, you can see that. So you know that model is the whole 4 nodes graph is the model. Now one node calculating the part of the model. Okay, node 1 is calculating top part of the model, and the another part of the model is calculating by node 4, another is node 2, another is node 3. But data, global data, they have access of the global data. Okay, so whole data they are accessing, and calculating the parameter or part of the model in this technique of the model parallelism. Now, finalized statement is that data parallelism trains the same model on different nodes, and every node in the system has a replica of the model to train using the subset of data. Where the model parallelism trains the different parameters of the model on different nodes. And for example, in the neural networks, and not only that parameter, neural network has a different layer, that one layer is computed by one machine, another layer is computed by another machine, like that. So that kind of parallelism is also is allowed, which is termed as a model parallelism. So everything is coming in the context of the distributed computing or parallel computing. So now let's give the topological description of the distributed machine learning technique. This first one, what I'm talking about, the centralized system, it's basically employ strictly hierarchical approach to aggregation, which happen at the single control location. So now you look into the figure here that basically there are multiple data, and that process and that basically assembling is done at a particular central node. So this kind of topologies later on will come very soon. That it's kind of client-server system where assembling is done at the server end. So this is just a client-server system, or you can say is a star topology. And now come to a decentralized system, which allow for intermediate aggregation. So aggregation can be done in intermediate ways. So now either with the replicated model that is consistently updated when the aggregation is broadcasted to the online nodes, such as topology can be a tree topology. Look into this picture here, that data aggregation can be done in individual intermediate nodes. And so earlier case, on the left-hand side, assembling is done at a particular node. Here, it can be done in any intermediate node of the tree. So this is a kind of decentralized setting. This is not a client-server setting, right? Here, intermediate node can act as a server like the centralized setting. Another is also distributed setting, which is called parameter server. You may have the parameter server that which basically partition the model, and that is shared over the multiple parameter server, which is showing in the figure C. Here, this is a multiple parameter servers are applied, and that parameters all together you can get the whole description of the model or get the output of the model. And finally, come to a general model, which is basically the most generalized or fully distributed system. In the fully distributed system, where each independent node, there is no dedicated node who can compute what. So in the context, all are independent nodes, and they can assemble the solution together where no specific role are assigned to a certain node. So this is more general problem, more general topology where distributed ML can be can be computed. So later on we'll discuss more about this, where pair-to-pair system or gossiping. We can have some slide on this. We can discuss later. So now let's discuss about the client-server models. I think we're everybody having the knowledge about the client-server model, where server holding the parameters to be optimized, and the data is available at the worker end or the client end. So client holding the data, the communicate to the server, server sending the parameter, client basically calculate the gradients and sending back to the server, and server is assembling that and again send back the improved version of the parameter to the client. So this is the client-server model, where the server act as the center coordinator to holding the process. So there is a pros and cons for this technique. You know that general centralized communication is needed here to communicate with the server by the clients, and the workload distribution is a good idea here, because parallelly each client can compute the gradients and finally send back to the server, and then the result available at the single point. This is server has the whole result, finally assembling the results, assembling the data collected from the slaves and get the results. but the tones are following. So communication bottleneck at the server. If you have a huge number of server clients, then this is the bottleneck at the server, and single point of failure. If server fails, then everything is gone. So these are the cones for this model. But anyway, this has a good point that there is one coordinator. The coordination among the clients is very easy, because so client will act as from the direction of the server, which is not happening for the peer-to-peer model or in the general distributed system. So now, let us discuss the distributed empirical risk minimization problem, where you see the equation, and that this minimizing this function fx, where it is equivalent to the basically finite sum of the function fj, and finite sum we are making basically over the d dimension of this problem, where x is the d dimension, and m is the number of the nodes, and fi is basically the local function which is located at the fj is the local function which is located at the node j. It's called the loss function, and which has the local data set at the node j. Okay, so now how do we design in the client server model? How do we compute this? So distributed risk management minimization problem, how do we do it in the client? So let's move in the next slide here. So here is a centralized communication model using client server. You can compute it by doing the finite sum technique. And here the model is following that that one end there is a server, other end there are the clients, and the client server communicate with the clients and to ask to compute with the local data available at the client's end, and clients basically calculate the gradients and compute with the data available and send it back to the server. Server refine the data, refine the parameters, and send it back to the client, and that basically is an iterative technique. So here nothing but the communication complexity is bounded by the iterative step. How many iterations you want to do, that's actually give the upper bound of the number of communication to execute this kind of model. Okay, so this technique is pretty easy, and you can compute this kind of distributed risk management minimization problem using the client server model. So this is the very easiest technique I think everybody can understand. So other distributed optimization for machine learning. Now the success of the machine learning model is mainly due to their capacity to train the huge amount of the data, and the distributed systems are the only way to process more data than one computer can store. But can also be used to increase the space at which the models are trained by splitting the work among the many computing nodes. So that's the general idea of the distributed system. And therefore, the most machine learning optimization problem can be the cost in the following way. So here is basically use the loss function. You can calculate a phi. So it's similar to that the technique as the minimum, the finite sum technique, where the loss function Li measures how far the prediction given by the parameter theta and the size of d is the true value y and the given sample x, right? So you are familiar with this kind of equations. So now where the model so we model this network as a graph of n nodes. Graph of n nodes not only is a client server model, it could be any general network, where the node I has the local data set di of size n. It means that the data set has n sample in total. So we assume that each fi is actually sigma is strongly convex, and that each component, so coming from the data set di and Li smooth in the parameter for a given timing sample. So distributed gradient method, let's discuss about that. So the aim of the distributed algorithm is to obtain a linear speedup. So that meaning that when run n nodes, the algorithm is n times faster than the first single machine algorithm. So this is actually the aim of distributed algorithm. Okay, So understand that. So if I give n number of nodes, so what is the time complexity for a single node? It linearly give the speed up, linear speed. So that means you understand in single machine take 10 hours. If I deploy 10 machine, it should take 1 hour. Kind of concept is actually looking for. But that's not always possible. So in the standard centralized setting, that all node can simply compute the gradient of the local functions, and the global gradient is computed by the server as the sum of the all local gradient. So this could achieve, provided the linear speedup is achieved, provided the machine has less number of samples. So that means there should have relevance that as long as there is a less machines than the sample, you can do that. Provide the network is the first enough. This approach in the linear speed up as long as there are less machine than the sample. Okay, so this is actually the goal to design kind of algorithm, but we may not achieve that. So now come to the general perspective. Now, if you have a general graph, you can compute this finite sum, and where basically if theta is an error model defined, theta is on the data set of the index I. So where basically each data set of the function fi is only accessible by the node I on the graph. So so ith node basically compute the fi functions. Now, after doing this, what happens? So then finally they have to assemble the data. So here, that example you see here that fi theta is to be calculated, which is the finite sum, and is a massive data set, use the multiple machine or core, and then actually the objective is to minimizing the communication and the local computation cost to do so. So now here is some work on this. If you're interested, you can have look on it. That using this technique, why not simple distributed algorithm? Why not simple distributing a simple single algorithm to all machines, to n number of machines? So here the accelerated gradient descent is implemented and proposed by this paper, where they have achieved that required kappa, so square root of kappa log 1 by epsilon full gradient computations to reach to the precision of epsilon. So here give the theoretical results to give the how many computations is needed to reach to the precision of epsilon in terms of the precision, and this has been discussed in this lecture. If you're interested, you can look in detail on this. So need to perform a distributed average over the network. This is the only work has been done here, but give the theoretical results in terms of the precisions, which is epsilon. So now the classical algorithm for distributed averaging here is following. How do you do this? Finally, the average has to be calculated in a particular node, right? Because or individual node also can do that. So now everybody calculate this, and they can disseminate the data. And if everybody having the data, they can compute it. So this is the one way. There are a lot of communication costs because everybody need to communicate with everybody, and then each and individual node calculate the average, right? But the technique in the master-slave technique, it can be done. You don't need to communicate with everybody. So communication cost. So now how much communication cost? This is a trade-off actually between the communication cost and the communication cost and the topology you want to use. So if you use a master-slave technique, so you want to calculate the average at a particular node, then you have to use a centralized algorithm, which could be a master-slave algorithm like that. So now, given a general graph, then what you have to do? Given a general graph, you have to construct either a spanning tree. Okay, so for example, here we construct a spanning tree, and one of the node you decide as the root of the node, root of the graph, root of the tree. Let's decide 4 as the root of the tree. Now, and also you have to decide the size of the diameter. So you choose compute the spanning tree with the diameter which is less than equal to delta, and then every node compute the value and send the data to the master, or which is the root of the spanning tree. right? In this figure, you can see that at first, node 4 is decided as the master or the root of the spanning tree, and then forward the data to the rest of the node, and then every node compute the value and send back the data to 4. So, and then 4 is compute the average, right? So for which here you know that to do so, the communication steps is it should be bounded by delta, because you consider the delta is 2 delta is the diameter is bounded by the 2 delta. So this centralized algorithm is centralized in the sense that there is one coordinator. Okay, that sense it is centralized algorithm, but this is happening in distributed way. So here this paper actually does. They have given the how many gradient steps and how many communication steps are needed. So they have mentioned that this square root of kappa log 1 by epsilon gradient steps and square root of kappa delta log 1 by epsilon communication steps are needed to do this, and which is essentially is optimal. And so once, if you are interested, you can look into it. But this technique also having a drawback. What is it? So this is the robustness. What is the robustness of the algorithm? So robustness is following that if node 6 fails somehow, then rest of the network is disconnected from this part, right? And whatever work is done by this part of the network cannot reach to 4. Right, so robustness is not guaranteed here, because even if the root node fails, then you are completely gone. You cannot compute it, right? So these are the drawback of this kind of centralized technique. So that is why you are looking for fully distributed system where if some part of the network is failed or some node is not working, then rest of the node give the results. Obviously, you have to sacrifice something. You may not get the whole data of the whole network, but you get something. And so that is why I like to discuss the gossip. I don't know whether everybody familiar. I give the introduction of the gossip, and which give the idea of how distributed setting can be developed with gossiping. So let's discuss, give some overview about the gossiping and exchanging data. So gossiping is basically a reliably disseminating data in the large-scale distributed system. So how it does is following, it is a repeated probabilistic exchange of information between two nodes. How it does is following that repetitions is also a crucial term. In principle, gossiping is an endless process of random choice of two members and subsequently letting those two exchange informations. So if I give one example, it will be clear to you that let's relate it to the epidemic. So what happened in the epidemic? That by which the disease is spread by infecting members of a group, right? If one member is talking to other, so this fellow who is talking has already infected and talking to other fellow, right? And that fellow also supposed to be infected now, which is happening in the COVID situation, right? So now, so the come in contact. So here also the gossip is that. So there is a space. Everybody. So the pair of nodes are meeting at a particular place and particular time. So whenever they're meeting, they're exchanging information, and then whatever the information they have exchanged, that is updated, and then those fellow who already got the updated information, they meet with the other fellow and exchange the information. That's the idea is called gossiping. Okay. So the gossiping concept is that the exchange of the information. So here is so individual process in the context of here information dissemination. What happened that two process. So in a distributed system here, the epidemic refers to the information dissemination where the node randomly chosen other members to which the information or that is the disease can be communicated, rather unless both are already contaminated. Okay, so this way data dissemination is possible. Recent advances have concentrated on the optimizing algorithm for improving this convergence speed and the number of the message to exchange. So that means recent development is that how first, so let's say there is a locality or you can see the theoretical point of view, there is a random node in a network, and they are in a dynamic in nature. In the wireless network, you can think that wireless devices are roaming around. So it's a mobile network. You can consider that two nodes are meeting each other and they exchange information. They have updated their information. Then again they meet. Those node will meet other nodes. They exchange the information, and again this way, then finally it will converge. Then whole network have the information. Okay. So the recent advance is looking for how first you can converge. So that means everybody have the same information. Okay, and how what is the number of the message exchange, such that you can you avoid the repetition. Let's say I met with someone, so now how you can design your algorithm and what is the technique such that repetition also can be avoided, right? So that is the perspective of the algorithm. So now here the convergence speed actually related to that. This is general model I am talking about, how information dissemination takes place. So now why it is needed in the context of the designing or optimizing here is that because individual node calculating these observations and then finally the decentralized algorithm. So now gossiping is completely decentralized algorithm, or it's like a peer-to-peer network, right? So two nodes are meeting each other, they exchange information, right? Or maybe through network also they can not necessarily they have to physically meet. So two nodes are neighbor of each other, they can talk to each other, right? They exchange information in a static network. What happened that 3 and 4 have an edge, they can exchange information. Like 1 and 3 has updated information. Now 3 and 1 exchange their information and 1 will be updated the information. Like 3 and 5 exchange their information, and 5 will be updated. So this way, not necessarily it has to be a mobile network. In static network is also possible. Gossiping can be done in a topology of general network. Right. So now, so in this space, what happened that so they are not individually connected with a root node in this network. What they have done is that so replacing theta I by the weighted average of the neighbor. So now they talk to the neighbor actually, and they updated the data with the neighbors. So that way, and finally you see the neighbors also updated with their neighbor. So that way, with the several round of exchange of information, each and every node should have information about the all other nodes, right? That's basically the convergence of the algorithm. So when every node, now you look in this figure, 4 has some information from the outside world, 4 exchange information with 3, 2, and 6, right? Now may have the 1 also have some information from the outside world, 8 also have information of the outside world, right? Now this outside world information, let's say, want to disseminate among the all nodes, right? Now how to do? So 1 will exchange information with 3, also with 2, right? In the next step, 3 and 2 exchange information with 4. 4 will have the information of 1 after 2 steps. Likewise, information of 4 will be disseminated in one step with 1, 2, 2, 3, and 6 because they are direct neighbor. And now next phase, 3, 2, and 6 exchange the information with 1, 5, and 9, right? So that way the information dissimulation, likewise, information of 8 will be exchanged with 9 and 7, and next round 9 and 7 exchange with 5 and 6. Next round that information will propagate with 3 and 4, and so on. The next round every node will get the information, right? So so this is the static node, or this is the concept of the gossiping. And finally, here the average sum they are doing, and with weighted sum, and then actually the finite sum is calculated with this kind of gossiping. Okay. So now in the synchronous gossiping, why it is synchronous? Again, there is a 2 model. One is synchronous and asynchronous. So now in this example, if you say that a whole global time you to decompose into discrete time unit, let's say step 1. So step 1, the synchronous system is following. That step 1, let's say 4, 1, and 8 got information from outside world. Step 2, what happened? Step 2, what happened that in the next round, 1 packet the information to 3, and 1 propagation information to 2. Same round, 4 information propagation will be made to 3, 2, and 6. Same round, okay, round 1. After round 1, this is the information propagation. Okay. So if it is happen to be a synchronous setting, then this is possible. In asynchronous setting, what happened that whenever a process wishes to forward the data, then only it can forward, otherwise not. So for example, 1 sometime got the information from outside the world, 4 got information from the outside, 8 got information from the outside world. Now 4 is willing to propagate the information with 3 and 2. That time that 1 has information propagation at the round 1. Actually, there is no general round. Now 4 that time is not willing to forward. Okay. After that, 3 and 2, one of them may forwarding the data to 4. That time maybe 4 is forwarding data to 2. It is so now individual node has a decision when to forward the data, when to talk to the pair. Okay, so that is called asynchronous system. So now that is why we are talking about the two kind of model. One is synchronous setting, another is asynchronous setting. Here in the synchronous setting, there is a result. Okay, all nodes are simultaneously acting based on the data and talking with the neighbor. So the main iteration will take place here. So theta t is basically calculated with the initial value of this initial value, and the typical assumption that W is W is basically the way we are talking about the symmetric W is stochastic matrix. And here, if anyone interested, please look into this paper. Now here what happens that this is as W is a symmetric doubly stochastic matrix, the eigenvalues are basically fall in the -1 and 1, and then ij gap between them is lambda, so gamma, and the mixing time for association Markov chain is basically gives this many iteration, okay, to dissimulate the data, this many iteration to reach the precision of epsilon. So every node will basically get the data with this kind of exchange technique using the synchronous gossiping. Okay, and this is the number of iteration, and everybody basically have the same information, and gossiping will end here, converge here. Okay, so this is one we are talking about the synchronous setting. So similarly, there is a asynchronous model where there is no synchrony at all. And optimal complexity here is basically this is the gradient step. This is the gradient step, and this many communication steps. Okay, and this many is communication steps. Because I'm talking about the synchronous setting, that is why communication steps are coming in the picture. In a synchronous setting, communication step defining has to be done some different way. So yeah, so now this we have discussed, and this is the work here. So gradient steps. This has been published, whether this is the gradient steps and this is the communication steps. The problem has been solved, and which is essentially is optimal. Okay, but not adapted in the machine learning technique. So this is what we are talking about so far, the distributed optimization. Okay, so now distributed optimization to be applied in the machine learning to actually get the objective of this distributed machine learning. So far we are discussing about the distributed optimizing, how we can do using the gossiping, or so far I have discussed how we can do with the client-server model in the centralized setting. So this is only synchronous, as I told you. So now here is there are trade-off between the there is a trade-off between the gradient calculation and the communication steps. So now here is one more basically comparison step. You can look into it here, that in the single machines the gradient steps are basically nm. N is the number of nodes, and m is the individual observation per node, and basically kappa is basically what? Kappa is basically is a parameter which is finite, which is used for the finite sum optimization. So for single step machine, this many gradient step, because in the single machine there is no communication. That is why communication is 0. And for the distributed setting or using the gossiping, you can see that gradient step is m square root of kappa, and whereas the communication step is basically square root of kappa by gamma. This is the work here, and another work is in the archive, the 2019, where the gradient step is m plus square root of m kappa, and whereas the communication step is kappa by gamma. So these are the advances in this distributed optimization technique. So now, now let's give some general idea of this. That how now, if you have n machine and m observation per machines, so for the single machine this is the result, and for so now you can reduce from this to this. Actually, the single machine having this kind of gradient steps, and the multiple machines, when you use multiple machines, or you can use n. So now is basically, rather it's basically a linear speed up, right? You understand that single machine computation is a function of n. When you apply n machines, so n is gone from this calculation. So n is gone from this calculation means you basically reduce the time, n times, fraction of n time you can compute the gradient steps. So which is basically the linear speed up for the well-defined, well-conditioned problem. This is essentially they have achieved in this work. Okay, so now finally I give some idea so far what I have done. So I just, what I have given is the idea of let me conclude some of the ideas. So far what I have given is that I give the idea of that how which kind of data parallelism and which kind of model parallelism is possible, and how you can apply this ClientServer model, and how in the client-server model, you know, there is a one server and other clients. And then finally, you can go for the general network. And general network, you have to do the distributed optimization. And then in distributed optimization, you can do using the machine learning, because now you merge with the, you can use the distributed optimization in the context of the machine learning. Then you can apply machine learning technique, which is in the inherent structure of distribution is possible. And then you can optimize, or you can get the value. One example is giving the gradient calculations, or sum of the average. And there are recent work which we highlighted that how much speed up is possible using, here is the table, how much speed up is possible. So for that, using the multiple machines or in our machines, is the linear speed up is possible. And these are the hardcore theoretical work with the function of the parameter kappa and gamma. And then finally, conclusion and challenges which is for to be doing is following that. So distributed machine learning is a thief ecosystem with a varieties of solutions, and that differ in the architecture, algorithm, and performance and efficiency. And why now there is a challenge in this context is that if you have a model, it's not that all model you can distribute, right? So that is the inherent structure of the model. That model you can distribute, and those problems you can solve using a distributed environment. So that is why it will differ with respect to the architecture, with respect to the algorithm, with respect to the performance and efficiency. Now, some fundamental challenges had to be overcome to make the distributed machine learning viable in the first place, such as finding the mechanism to efficiently and parallelize the processing of the data while computing the outcome into a single coherent models. And now that there are other industry grade system available, and in view of the overgrowing attitude of tracking the more complex problem with machine learning, distributed machine learning is increasing because of the norm and the single machine solution and the exception similar to how the data processing in general are developed in the post decade. So therefore, finally, we'd say, however, that still there are many open challenges and that are crucial in the long-term success of the distributed machine learning. So in conclusion, I would say that so because of the model size is increasing, so the biggest question is that. So far I have given the general description of the algorithm here, that in the general model is a very simplest model we are looking for here, that like finite sum technique and gradient descent problem, right? Now the practical problem, you can look into it. This is as a theoretical prospect. Now you can look at the practical problems, and there are millions of parameters. Now how to decompose into different machines and finally communicate them, assemble them, and get the results is a big challenge. Okay, so and this you cannot give a general technique because different techniques has different way whether you can decompose the parameter into different machines or not. So that is why generic technique given is very difficult. It is a very problem specific for a particular optimization problem which are available in that context. You can decompose into different models and you can speed up. So that's all for this domain is concerned. And yeah, so finally, thank you, and thank you for your attention. I can take questions if we have something. So Ashok, any so far anything or any chat question is appeared or anything here? Ashok, your voice is not coming.
Yes, please. So we can take some questions. Any questions? Hello. Yes. Dr. Murthy, any question?
Okay, so thank you all of you.
Okay, yeah. Thank
for
you
your
Partha.
attention.
Thanks. Okay, Partha, thank you.
Okay, so then I'm leaving. Bye bye to all of you.
Okay, yeah. So please join at around 2:45 sometime.
Okay.
So
Okay then.
We'll take feedback from the participants.
Thank you, sir.
Thank you all of you. I'm leaving the meeting. Ashok.
Okay, fine. Thank you. So we'll have the next this one exam from 2, everyone.
Yes, sir.
Okay. Yeah, so for a time, so now we'll stop and then we'll have the exam from 2. Okay, so the meeting will be on. So if you have any questions during if you are facing any problem, then you can write to me on chat. Or you can, okay, chat will be easier for me.
Find the exam link.
Sorry?
The exam link will be shared at which particular platform?
It will be on Google Forms. It will be on Google Forms.
The link will be shared in the meeting chat window or the WhatsApp group or both.
Your voice is not clear. Can you speak a little louder? Who is this?
Sharing in
Sir, this is Jagdish Saini.
Yeah, Jagdish Raj. Yeah.
Yeah, sir. Sir, I just wanted to know whether the link to the exam will be shared in the chat window or in the WhatsApp group or both.
I'll do it in both the places.
Okay. Thank you, sir.
Thank you, sir. Thank you so much.
Okay. Welcome.
Exam
So, yes.
2 o'clock.
Sorry?
Sir, 2 o'clock, sir, exam?
Dr. Rao, yeah, I'm not able to hear you. Can you speak a little louder?
Sir, it is 2 o'clock. 2 o'clock exam. 2 o'clock?
Sorry?
2 o'clock, exam 2 o'clock?
Sir, he's asking whether exam will start at 2 o'clock.
Yes, exactly. I've already sent a mail. I've sent a mail also, and I've sent it on WhatsApp group. I think you all have got it, no?
Okay, thank you.
Yes. It's confirmed. I've sent on mail several times. So 2 p.m. exactly. 2 to 2:45, and then please today. So you switch on your videos today. So we just want to get your feedback after the exam, so that tell us how we have done, how we have fared. Okay. Okay, then I'll stop now for the timing. It will be open for 45 minutes. 45 questions, 45 minutes, and most of the questions will be true false kind of thing. So it will be simple test, not a very good one. Okay. Okay then. Thank you.